Right, guys, I'm feeling some hardcore sunk cost fallacy right now. I sort of had a bit of a part one plan where I was going to basically just bombard you with a bunch of fluff about how induction works. But we're just going to get straight into it. We're actually going to go over an example and we're going to see how you can do it. Alright, so before we get started, we might go through the first one a little bit slow just to really hone in on sort of the idea of induction, which I think is going to be divisibility. And then for the next few, we'll just sort of breeze through them, clarify what the differences are going to be, and just so you know what you're in for, I guess. So first I want to come up with a conjecture. I want to say that 5 to the n plus 2 times 11 to the n is divisible by 3. And I can write this as equaling 3a, where a is some integer, some number. And this only applies when n is a positive integer. So first I want to prove for the most basic case, so when n's 1, I guess. So 5 to the 1 plus 2 times 11 to the 1 should be divisible by 3. So clearly a has a number that it can be, which makes this equation true, and that's 9. Now we have step 2 to assume that p of k is true. So I'm using another letter here to represent n, k, where k is just some number. I don't know who decided that, because k is not the first letter of the word constant, unless you are feeling a bit quirky. I don't know. So k is some value within domain of variable n. Therefore 5 to the k plus 2 times 11 to the k equals 3a is true, given I have substituted k in for n. So k is just some number. And we assume this is true. So now I'm assuming this is going to be correct regardless. Now I'm going to write out what it would look like for k plus 1. So this is assuming we get that number that k was and then add 1 to it. And that's still a part of the conjecture that it should be true. If I can prove that this new value is correct, given that k itself is correct, I could say if k was 1, then 1 plus 1, which is 2, would be true. And if I can say that 2 is true, then therefore 3 is true, because 2 plus 1, k plus 1, whenever k is true, the next one's going to be true. And that just sort of has a knock-on effect for every possible integer. So given that, I could write it as 5 to the k plus 1 plus 2 times 11 to the k plus 1 equals 3b, where b is another different integer. And I can expand that into 5k times by 5 to the 1, and that's just because of exponent laws. So now I'm going to say that that is true, as before, and using that knowledge, try and prove that this next one is true. So I can expand it, as we mentioned, using exponent laws, and I'm going to do something a bit funky here. So I've gotten 5 times by 5k from up here, and then I'm going to add 5 times 2 times 11 to the k and subtract 5 times 2 times 11 to the k. So I haven't done anything else. That's like adding 0. I've added it and subtracted it. Nothing's changed. And then I've got the rest of the equation at the end here. And why am I going to do that? Another distributive property law where I can sort of expand the brackets, or I guess do the opposite, factorize the brackets. I can take 5 out of all of these terms, which leaves me with this, which I don't know about you, but looks pretty familiar. And then I'm left with, this gobbledygook at the end here. And because this seems familiar, because this was this, and we're assuming this is true, so I can substitute that for 3a. So I know this is 3 times some number. And then I've got the rest of this still. And what am I going to do with that? I'm going to contract it as much as I can. So then we've got 5 times 3 lots of a plus 12 times 11 to the k. And what is 12? It's 3 times 4. Therefore 3 times 5 lots of a plus 3 times 4 times 11 to the k means that I'm going to have all these integers and multiply them by 3. So if I divide by 3 again, I'm just going to get back to the original integers. So all these terms are in fact divisible by 3 in k plus 1. So therefore the next induction example will be a proof of series. So the conjecture this time is going to be that the sum of 3 to some power is equal to a half of 3 lots of n take 1. So let's just first prove that it works for p of 1, so when n is 1. So using the uppercase sigma for summation, obviously, and if you haven't done that yet, then I don't know why you're watching something on induction, but it becomes 3 to the 1 take 1 is lots. There's 3 to the 0, which is 1. A half of 3 to the 1 take 1 is a half of 2, which is also 1. So therefore, both the left-hand side and right-hand side of this situation is true. So p of 1 is right. Now we're going to assume that for some number k that it is going to be true. So I now want to prove that it is k plus 1 is true when I know that k is true, as we stated before. So let's try that. So given that this statement initially we made is correct, let's now try and prove that the sum to k plus 1 can be true for a half of 3 to the power of k plus 1 take 1. So let's write this all out. I can write the sum of k plus to k plus 1 of 3I take 1 as what we had before, just to the k plus the next term, which is going to be 3 to the k naturally. And that is going to equal the other side plus 3 to the k. And this is because we know that this small part in the middle here, which we've already established up here, is equal to this. We know this is true. We're assuming that that's completely correct. So I can substitute this right hand side in for what was here and just add 3 to the k for it, which then we know is the summation to k plus 1. So we've got a better way to write it now. So in this circumstance, I'm now going to factorize it, which can be expressed in these terms, which is a half of 2 times 3 to the k plus 3 to the k take 1. And by simplifying that down, it eventually becomes a half of 3 to the k plus 1 take 1, which in this circumstance is the next term on. The next circumstance is for matrices. So let's first prove that this conjecture is correct for the first circumstance. So that matrix to the power of some n is equal to this other matrix, which is not to any power but has terms inside which are to the power. So the entire matrix to the 1 is equal to, well, 3 to the 1, 1 to the 1, 0, and 2 to the 1. So that's pretty obvious that that's right. If we just sort of simplify it real quick, there we go. Therefore, very easily seen. I don't know who wrote that in there. There was a gremlin actually who made this PowerPoint for me before, and I had nothing to do with this, so I've got no idea what's going on right now. I'm just reading it as it comes on. Therefore, both the left-hand side and the right-hand side are right. Yep, we know that. So now we're going to assume this equation that we've written is true. So now we're going to try and prove it for k plus 1. So we assume this is true, and now we're going to write it out for k plus 1, which, given that, looks like the term at the bottom here. So essentially, this matrix now to k plus 1 instead of just k is equal to this matrix with all the terms literally added add 1 to. And then I can express k plus 1 using exponent laws like this, where it was our original to the k multiplied just by another one again. And I could do the same thing, but this matrix is going to get absolutely absurd then if I keep doing that. So let's have a look here. So we assume that's true, and what I can do here is basically substitute this bit by expanding. So we expanded using the exponent laws from k plus 1, and we know that the k here is equal to this over here. So I can rewrite that as the k bit being just with the numbers on the inside to the k, and multiply it by this once more. And if I do matrix multiplication, no, I'm not going to tell you how to do matrix multiplication. If you don't know how to do matrix multiplication and you're watching a thing on induction, I might ask what on earth you're doing here. I'm just kidding, of course. By multiplying, we have some really ugly maths here. We can simplify that down to 3 to the k plus 1, 3 to the k plus 1 take 2 to the k plus 1, 0, and 2 to the k plus 1, which checks out. If we go back here, we know that this to the k is equal to these numbers to the k, and then if we do it to the k plus 1, then they all have 1 added to them. Either trust me on this or do all the working out yourself, or I don't know, read what's written on here. We can say that given P of k is true, P of k of 1 can be derived, and thus is also true within the condition. Now, I was going to have a quick spiel about simple inequalities, but they're a little bit hard to explain, so I've got to write an actual script for that bit. So just hold tight and I'll post that in a separate video.